And this lecture is only about the capacitive voltage source. The capacitive current source is also discussed in the book. But as soon as you know a procedure, you can do any optimization yourself. That's the intention that we have with structured design, of course. So the optimization for a capacitive voltage source. So the situation is like this. We have a source, VS, a voltage source, with a source capacitance CS, and there I attached the noise model of the NMOS, of the MOS transistor. You remember two correlated sources, B times IN and D times IN. And the gate referred noise, the gate current referred noise, ING. So the equations we know already, so I can just simply put them there on the screen, and so it's B and D, and the spectral densities of the two sources, the current spectral densities. So what we want is to have all the noise contributions translated into a voltage noise in series with the signal source, because then that is the way to talk about a signal to noise ratio. Signal Vs and noise Vn should have the same representation. If we have a signal which is voltage and a noise which is current, we cannot say there is a signal to noise ratio, because the signal to noise ratio should be dimensionless. So the first case I would like to discuss with you is that we ignore the 1/f noise, just for the sake of simplicity, and later we will also study the influence of the 1/f noise, and we will ignore the DC current to the gate, because usually it can be ignored because it's extremely small, but of course it is interesting to know what happens if it becomes relevant. So there will be a question for you then. So there he is. The spectral density after you substitute the parameters B and D is 4kT n gamma divided by Gm times 1 plus the total input capacitance at shorted output divided by CS squared. That is what remains if you substitute B and D into the equation that we had before. And now it is interesting because we see CISS in one equation and GM in the other one. So why don't we make it more simple and replace GM also with CISS? Because it can be written as 2 pi FT CISS. And then you get the last part of this equation, simplifying the whole thing to SVN equals 2kT n gamma divided by pi FT CISS times this term in which is CISS as well. And then again, we see a function of CISS. And if we differentiate this function for CISS, then we could find an optimum for CISS under the condition, of course, that FT does not depend anymore of CISS. And that happens if we do exactly the same scaling as we did before. So similar with the resistive source, we increase W and maintain the inversion coefficient. If we do so, FT does not change, but CISS does. It increases with the width. So FT is constant because you can speak of, let's say, if you make the width 2 times larger and you maintain the inversion coefficient, it's exactly the same as placing 2 transistors in parallel. And then the FT, of course, of the parallel connection is still the same, but you have 2 times more current. So we maintain IC means that with increasing width, we also scale the current. Under that condition, FT is a constant, and the only variable thing in our expression is CISS. And that you can differentiate and you can find an optimum. An optimum, and the optimum occurs if CISS is equal to the source capacitance. That is very simple. But now a question to you. I said, let's forget about the gate noise. But what in which, what if we don't forget about it? In which way will a DC gate current affect the noise spectrum? That's a poll question. So we have three answers quite close to each other. There's no effect is 35%. There is a noise increases with 3 dB per octave if the frequency decreases, or for decreasing frequency, that's 28%. And the noise increases with decreasing frequency for 6 dB is 38%. And I'm happy to see that the majority, let's say not the majority, but the biggest number is okay. So it increases with decreasing frequency with 6 dB per octave, because we just have a current flowing over a capacitor. So this current, this IG, must be, for low frequencies, sees a higher impedance, and it goes with the characteristic of the impedance, which is 6 dB per octave. That is the reason. It's not 1 over F noise. We ignored the 1 over F noise, but we don't ignore the gate noise. So you can even think if it would be the gate current plus 1 over F noise, we would even see a part of 9 dB per octave. So that's the answer to the question. Now let's go to the second case. I will click the poll away. Let's go to the second case and account for the 1 over F noise, and again ignore IG because we now already know what IG will do. And then we write the FL, the corner frequency of the 1 over F noise, as a function of FT, and that is a constant times FT, as we have discussed before, and this constant depends on the process. So I gave it just a name alpha. It's not a general name. I just put some constant there, whatever you name it. But it's important for us to know that it is related to FT. So if we are doing the same thing, we maintain the inversion level, then the inversion level sets FT. If we are working at low inversion, we have a low FT. If we are working at high inversion, we have a very high FT. And if we are working at about critical inversion, you probably have the highest FT possible in your process. Maybe it will go a little bit higher as long as GM increases. But as we have seen, GM doesn't increase that more if there's a lot of velocity saturation and vertical field mobility rejection. So this is a process parameter. So this is just a fixed thing. So it doesn't change with CISS if we are going to change the width and maintain the inversion level. So we do exactly the same as we did in the previous one. We increase the width, maintain IC, and then we find, of course, the same optimum, but probably at a lower current. Because if the 1 over F noise becomes very important for you, you are not going, you have to go to, let's say, weak inversion. And at weak inversion, the FT is less, and which means, and CISS is still the same, which means that the spectrum of your noise is higher because FT is in the denominator. So there's also a possible showstopper value, possibly a showstopper value. I didn't put it here in the sheet, but this is how it works. I think the procedure is very important for us. And the derivation of the formulas, you could even leave it to SlideCap because it can do symbolic integration and differentiation. And that is what I would like to show you, how such a setup can be done. And then we do it for the resistive case. And I'm asking you to do it yourself if you want, if you think you need it for the active antenna. For the capacitive case, you know now how it works. And I will show you the tips and the tricks with SlideCap and also LT-Spice, how to do this noise analysis.